Hello, everyone. This is the continuation of our lecture on vectors, which we didn't quite finish last time. So just a quick recap of what we have discussed. So we started to talk about vectors, and we said that vectors are often important when we're dealing with two-dimensional motion. In our next lecture, we will look at projectile motion. And then when we talk about forces, we will also use vectors. Vectors represent the magnitude or size of the quantity as well as the direction. And usually vectors are represented by either a bold font or an arrow above the symbol. So this is the vector representation for velocity, acceleration, displacement. And this week we will talk about forces as well. We draw vectors as arrows, where the length of the arrow corresponds to the magnitude or the size of the quantity represented by the vector. And because vectors are used to indicate direction, the direction of the arrow indicated by the arrowhead, where the arrowhead is pointing at, gives us the direction of the vector. When we say negative of a vector, it means that the directions are opposite. So these are two vectors at opposite directions, meaning this top vector is the negative of the bottom vector. Because vectors give information about both the magnitude and direction of the quantity, we say that two vectors are the same only if they have the same length, such that those two quantities have the same magnitude, and the vector should also have the same direction. So the vector, the arrows representing the vector should be pointing in the same direction. So in this example, these two vectors here are the same. We also learned last time that when we multiply a scalar, meaning when we multiply a number, an integer, to the vector, the effect of the multiplication is either to increase the size of the vector if you're multiplying with a number greater than 1, or decrease the size of the vector if you're multiplying with a number that's less than 1. The sign of the number or the scalar that is being multiplied to the vector could influence the direction of the vector. If the number or the scalar quantity is a positive number, then the direction of the vector would be the same as the original vector. But if you multiply a negative number or a negative scalar to a vector, the negative sign in the number has the effect of flipping the direction of the vector. So here's an example where the original vector v was multiplied with a negative 2. And you can see here that the direction of the resulting vector is opposite the direction of the original vector. So we learned that last time. We also learned last time about resultant vectors. We defined the resultant as the vector that is the result of adding or subtracting two vectors. And we learned that if the vectors are pointing in the same direction, then we add these two vectors to get the resultant. And the direction of the resultant would be the same as the direction of the two vectors that are being added. On the other hand, if you have two vectors at opposite directions, the resultant vector is obtained by subtracting these two vectors, taking note of our sign convention where A negative vector is one that points to the left or to the negative x-axis, to the west downwards, negative y-axis, or south. Of course, a positive vector then points in the opposite directions of the negative vector. So in this case here, you have two vectors, one pointing to the right. This will be a positive vector, and another one that's pointing to the left. This pointing to the left vector will be a negative vector. So that when you get the resultant of these two vectors, you'll have a negative vector here essentially being added with a positive vector. So in essence, you are subtracting these two vectors. The direction of the resultant vector then depends on which vector has a bigger magnitude. So in this case, we can see that the vector pointing to the left has a greater magnitude or size compared to the vector pointing to the right, and therefore it makes sense that the resultant vector is pointing, it will be pointing to the right. We also learned we also learned the graphical method of adding vectors. We said that in graphical method, you have to literally draw the vectors that you add up together. And the way to draw them is to join them sequentially head to tail. So here's an example we looked at last time where we're adding vector A with vector B. We draw the vectors such that the tail of vector B joins with the head of vector A. So we draw vector A and the tail of vector B joins up with the head of vector A. The resultant vector then goes from the tail of vector A to vector B. And when you're adding vectors, it's important not to flip any of the vectors that you're adding. You only flip the vectors if you have a negative vector, so that, as we said, the effect of the negative sign is to flip the direction of the vector. So here you're subtracting vector B from vector A. Vector B is therefore negative. Notice how you draw the vectors again using the head to tail method. Vector A joins up with vector B such that the tail of vector B connects with the head of vector A. But notice how the direction of vector B is flipped compared to the original vector here. It's because of the effect of this negative sign here, which essentially is this subtraction that you are doing. The resultant vector again goes from the tail of the first vector to the head of the last vector. But as I mentioned last time, the graphical method can be quite tedious because you have to draw the individual vectors with the correct magnitude or size using a ruler. And then to find the resultant vector, you'll also have to use your ruler to measure the length of the resultant vector. So if you're dealing with more than two vectors, it becomes quite tedious. So the other method that you can use when adding and subtracting vectors is called the component method. So here now we'll learn how to use the component method to add or subtract vectors. Let's use this vector drawn here as an example. It's a force vector represented by this symbol F. This vector is at an angle theta relative to the x-axis, meaning, as you can see here, this vector is diagonal relative to the x-axis. the thing to remember is that any diagonal vector can be broken down into its vertical and horizontal components. The horizontal component is the component that is along the x-axis, and that's why it's also called the x component. The vertical component is along the y-axis, and that's why it's also called the y component. The vertical and horizontal components of a vector are always perpendicular to each other, right? So here is the horizontal or x component. Essentially, you get that by projecting the arrowhead representing the vector onto the x-axis, and then you draw the vector along the x-axis to give you the horizontal or x component. The y component will then always be perpendicular to that x component. And notice how the tail, the head to tail rule for drawing vectors is also followed, such that the tail of the vertical vector joins up with the head of the horizontal vector. So here you can see clearly that the horizontal component and the vertical component are perpendicular with each other, and so together with the resultant vector, the diagonal vector, they make up a right-angled triangle. So this is always a 90-degree angle here. Okay, the question is, how then do we calculate the horizontal or x component and the vertical or y component of any diagonal vector? So we'll need some trigonometry to calculate the horizontal and vertical components of a diagonal vector. As I mentioned, the diagonal vector, along with its components, horizontal and vertical components, will always form a right-angled triangle. Okay? And that allows us to use trigonometry to determine the horizontal and vertical components of the diagonal vector. There's this rule that says that the sine of the angle of a right-angled triangle is equal to the side opposite that angle divided by the hypotenuse of the right-angled triangle. I usually use the acronym SAW. SAW stands for the sine theta is equal to opposites divided by hypotenuse. Okay. So if we apply this trigonometric rule, we can then find the vertical component, which is the side that is opposite the angle in our right-angled triangle. So sine theta will be the side opposite, which is the y component Fy, divided by the hypotenuse, which is the diagonal vector F. Since we are after the y component, we rearrange this equation to have the y component being equal to the diagonal vector, which is also the resultant vector F times sine theta. Just to put numbers, okay, if the diagonal vector is 20 newtons and the angle is 30 degrees, then the y component is calculated by multiplying the diagonal vector, which is also the resultant of the x and y components, multiply that with sine 30 degrees, and that gives you 10 newtons for the magnitude of the y component. A final check will be to see the sign, whether the y component should be positive or negative. All right, notice how the y component vector is pointing upwards, so that should be a positive plus positive 10 newtons. Right, this trigonometric identity cosine theta gives us the side that is adjacent to the angle theta divided by the hypotenuse of the right angled triangle. So if this is the theta angle of the right angled triangle, the side adjacent to that will be the x component. And of course, the hypotenuse is the diagonal vector, right? So by using this cosine theta identity, trigonometric identity, which I sometimes use the acronym CA, C stands for cosine, theta is equal to the side adjacent to the angle divided by the hypotenuse. Okay. Cosine theta will therefore be equal to the x component of the diagonal vector because the x component is adjacent to the angle theta divided by the hypotenuse of the right angled triangle. Okay, we're after the x component, so similarly we rearrange this equation. The x component will therefore be equal to the hypotenuse times cosine theta. In this particular example where we assigned that the hypotenuse is 20 newtons and the angle is 30 degrees, the x component will therefore be 17 newtons now. Yep. And again, just a quick check whether 17 newtons should be positive or negative. Notice how when you draw the x component, the vector is pointing to the right. So that will be a positive 17 newtons. Okay, so when you have, so to have the correct directions for your x and y components, you start with the diagonal vector that's given. Okay, project the head of the arrow representing the diagonal vector, project it to the x-axis. Draw your x component from the tail of the diagonal vector to the projected point. And notice how the arrowhead for the x component is pointing to the right. Okay, so that will be a positive 17 newtons. And for the vertical component, the tail of the vertical component should join with the head of the horizontal component. And that's why you know that the vertical component should be pointing upwards, and therefore it should be a positive 10 newtons for the vertical component. Right. So if we now put the direction together with the magnitude, the y component will be positive 10 newtons in the upward direction or plus y direction. We indicate the plus y direction using this j hat vector, and I'll talk about the j hat vector in a bit. And for the x component, we have 17 newtons in the positive x-axis direction or to the right. We represent I hat. We use I hat to represent the positive x-axis direction. Okay. So what are these I hat and j hat? The I hat and j hat and an additional k hat here are what we call unit vectors. Okay. Unit because their magnitude is equal to 1, right? Unity that represents a number 1. And unit vectors are used to indicate the direction of the vector components. Because the magnitude of unit vectors is 1, it doesn't really affect the size or the magnitude of the actual vector itself, but we use them to indicate the direction. So this diagram shows us that the vectors along the x-axis will use the unit vector I hat. Okay. If the vector is pointing to the right, then of course that's a positive I hat. Pointing to the left will be a negative I hat. The j hat vector represents the direction along the y-axis or up and down. If it's a positive direction, meaning your vector is pointing upwards or to the plus y direction, then we use a plus j hat vector. If the vector is pointing downwards or towards the negative y direction, then you have a negative j hat vector. And just for completion, in a three-dimensional space, the vector direction representing the z-axis is k hat, right? So into the page or towards the negative z direction, we'll have a negative k hat unit vector, and the direction out of the page or along the plus z hat direction will have a plus k hat vector. So if you have a vector that has x, y, and z components, you can indicate the directions of the x, y, and z components by using the I hat, j hat, and k hat unit vectors. So we'll be using I, j, k unit vectors quite often, especially when we go into forces. Right. So now that we've learned how to get the horizontal and vertical components of a diagonal vector, let's now see how we can add and subtract two vectors using the component method. So here we have an example showing two vectors, vector A, which is this blue arrow here, and vector B, which is this pink arrow. What we want to find is the sum of vector A and B. Vector A makes an angle theta1 relative to the x-axis. Vector B makes an angle theta2 relative to the positive x-axis. So the first step is to find the horizontal and vertical components of the vectors that you want to add. And let's start with vector A. Okay, x component of vector A, again, you get the, well, if you use the trigonometric identity Ka, right? Because we're after the x component, then cosine of the angle theta1 will be equal to the side adjacent to the angle, which is the x component, divided by the hypotenuse, in which case we rearrange that as the x component is equal to a cosine theta1. So graphically here, you can draw that by starting at the head of the diagonal vector, project that onto the x-axis, and draw the x component from the tail of the diagonal vector. So this is the x component of vector A. Right, and for the y component of vector A, you draw that from the head of the x component to the head of the hypotenuse, or the diagonal vector. Okay, using the trigonometric identity, so sine theta is equal to the side opposite the angle divided by the hypotenuse. The y component is equal to a sine theta1. Okay, and you do the same thing for vector B. For the x component of vector B will be b cosine theta2. If you draw it in the diagram here, you start from the head of vector B, project that onto the x-axis. That gives you the x component. And then for the y component, similarly, the y component for vector B equals b sine theta2, following the identity sine theta equals opposite over hypotenuse. The y component is drawn from the head of the x component to the head of the diagonal vector. And notice that in both cases, the x and y components are always perpendicular to each other. And together with the hypotenuse, they always form a right-angled triangle. Okay, So that's the first step, is to find the horizontal and vertical components of the diagonal vector. Okay, once you have found the horizontal and vertical components of the diagonal vector, you can completely forget about the diagonal vector, okay, and just consider the x and y components, right? So here, I'm only showing the resulting x and y components for vector A and x and y components for vector B. Okay, you can, if it helps you, you redraw the diagram without the diagonal vectors, then it's easier to see that you're now dealing with either horizontal vectors or vertical vectors. And it's then easier to see to see which, I mean, it's now easier to add components of your vectors, okay? You can only add horizontal components together and vertical components together. Okay, so let's add the x or horizontal components together. Notice how they are both pointing to the right, okay? And therefore, both of them are positive. Okay, we add them together, ax plus bx, and expand that addition using the equations that we determined using the trigonometric identity. For the y components, okay, for the y components, notice that they are pointing in opposite directions, right? The y component of vector A is pointing upwards, which means it's positive, whereas the y component of vector B is pointing downwards, which means it's negative. Therefore, if we add these two vectors, one of them will be negative, the other will be positive. Effectively, we are then subtracting the y component of vector B from the y component of vector A. Okay? And vector B has a negative sign because, again, vector B is pointing downwards. And effectively, we are then subtracting these two vectors. And we can expand the subtraction using the equations for the y components that we obtained using the trigonometric identities. So you have here ay minus by. Okay, once we've added the x components all together and then added the y components all together, you will find that you will now have just a single x component and a single y component, right? So the single x or horizontal component came from adding the two horizontal components, and the single y component comes from adding the two vertical components, taking note that one of them is negative. Okay. So we are now back to this right angle triangle with a horizontal component, a vertical component, and these two components are perpendicular to each other. The resultant vector is then the hypotenuse of this right angled triangle. Right, so once we've calculated the resultant vector, we have effectively found the answer for vector A plus vector B. Now the question is, how do we find this resultant vector if we know the horizontal and vertical components? Right. Because we know that the horizontal and vertical components are always are always perpendicular to each other, and the hypotenuse of this right angle triangle is the diagonal vector or the resultant vector, we then need to find the hypotenuse using trigonometry. Okay? So this is what we want to find. That's the resultant vector that we want to find. And Pythagoras or Pythagoras theorem tells us that if you have a right-angled triangle, the hypotenuse of that can be calculated by this equation, square root of x component squared plus y component squared. So just for the sake of an example, let's assign some numbers, well, which we've, let's say the x component is 17 newtons and the y component is 10 newtons. The the diagonal vector can then, or the hypotenuse of the right angle triangle can be calculated as square root of 17 squared plus 10 squared. That gives us 20 newtons. So that means that the hypotenuse is 20 newtons. The resultant vector will therefore be 20 newtons for the magnitude. Now for the direction, we need to calculate this angle here. The angle is usually measured from the horizontal or x component. Okay, to calculate the angle, we use the trigonometric identity, which says the tangent of the angle is equal to the side opposite the angle divided by the side adjacent the angle. So the side opposite the angle is the y component, and the side adjacent the angle is the x component. Tangent theta will therefore be equal to the y component divided by the x component. We want theta, not tangent theta. So to get rid of this tangent here, we use the arctangent. So arctangent of the y component divided by the x component will give us the angle. Okay. The y component is 10 newtons, the x component is 17 newtons, so that will be 30 degrees for the angle. Okay, once you've determined the direction, the angle theta from the trigonometric identity using the arctangent of the side opposite the angle divided by the side adjacent the angle, we usually measure the angle from the positive x-axis. Okay? So the last check you need to do is to see whether the angle you've calculated is being measured from the positive x-axis. You're probably familiar that the mathematical space can be divided into 4 quadrants. So this is the first quadrant, second quadrant, third, and fourth quadrant, right? If the resultant vector is in the first quadrant, then you can easily calculate for the angle theta. Whatever angle you solved here will just be the final angle that you will give as the answer. If the angle if the resultant vector is located in the second quadrant, the angle that you calculate using this trigonometric identity is usually measured from the negative x-axis. So in that case, the final angle that gives the final direction should be 180 degrees minus the angle that you've calculated. Okay. If the resultant vector is in the third quadrant, as shown here, the angle that you calculate using this tangent theta function is measured from the negative x-axis. Okay, so to give the final angle, you should do a 180 degrees plus the angle that you've calculated using the trigonometric identity. And finally, if your resultant vector is pointing this way in the fourth quadrant, then the angle that you've calculated using the trigonometric identity is measured from the positive x-axis. Okay, so you can, but but notice, but it's different from the first case, because in the first case, the angle theta is measured from the positive x-axis to the resultant vector in an anticlockwise direction. Whereas for the fourth case, where your resultant vector is in the fourth quadrant, the angle theta is measured from the positive x-axis to the resultant in a clockwise direction. Therefore, the final angle will be a negative of whatever angle you've calculated using the trigonometric identity. So you can say the final angle is equal to negative theta, or you can also do 360 degrees, take away the angle that you've calculated using the trigonometric identity, and that gives you the final angle as the answer. So we use this convention of measuring the angle from the positive x-axis mostly for uniformity. But yeah, I would encourage you, for example, in the test to write down your working. If I see that you've calculated the angle correctly using the trigonometric identity, the quoting or writing the final angles could usually be forgiven. But for instances, for example, in the workshop this Friday, when the answers are given, the answers for the final angle are measured from the positive x-axis. All right, so just to wrap up this lecture on vectors, let's look at this example. An explorer walks 22 kilometers in a northerly direction and then walks in a direction 60 degrees south of east for 47 kilometers. What is his resultant displacement from the origin? So here are some answers that we can derive. So you can either pause this video and try to solve this problem. But yeah, I'll continue on because you can always pause the video if you want to try it yourself first. Right, so let's draw the scenario. The explorer walks 22 kilometers in the northerly direction, so we represent that by vector x1. The blue arrow here, it's pointing directly up north, and that's 22 kilometers. So we can represent this vector x1 by the magnitude 22 kilometers, and the angle relative to the positive x-axis is 90 degrees. So that's the direction, 90 degrees. Then he then walks in the direction of 60 degrees southeast for 47 kilometers. So we represent that angle, that vector as x2, right? 42 kilometers will be the length of this red arrow representing that second vector. And the direction is 60 degrees south of east. So south of east will be, yeah, so you see here, south of east will be below the negative, below the positive x-axis. So that will be a negative 60 degrees. If you're measuring, say, if you're measuring the angle like this way in a clockwise direction. Also notice, as I've mentioned in the previous slide, this diagonal vector is in the fourth quadrant, and therefore the angle will either be negative 60 degrees or 360 minus 60 degrees. What we want to find is the resultant vector, which will give us the displacement from the origin. So the resultant vector is shown by this green arrow here. You draw it from the tail of the first vector to the head of the last vector. That will give you the displacement. Right. Yeah, systematically, it's really just recipe, step 1, step 2, step 3, so on. As I've said, if you have vectors that you want to add, the first step is to identify the x and y components. It might be useful to make a table like so you can write down what are the x and y components for each of the vectors. Then you can easily see which vectors to add to get the resultant vector later on. So for the first vector x1, it's directly straight upwards, so there is no x component, but there is only a y component, 22 kilometers. For the vector x2 is a diagonal vector, therefore it should have an x component. The x component will be the projection onto the x-axis. So as I have been mentioning a lot earlier, you start from the head of the diagonal vector, project that onto the x-axis, and you then draw the x component from the tail of the diagonal vector to the projection point along the x-axis. Okay. Automatically, you see that this x component is directed to the right. So you already know automatically that the direction should be plus I hat or plus x direction. For the magnitude, you use the trigonometric identity. You want to find the side adjacent to the angle. Therefore, you use the cosine theta function, which then leads you to hypotenuse times the cosine of the angle. So that will be 47 times cosine negative 60 degrees. You'll end up with a positive 23.5 kilometers, which is consistent with the direction of the arrow you've drawn here, which is pointing to the right or plus I hat direction. For the y component, the y component of the x2 vector is then drawn from the head of the x component to the resultant vector. Notice how you have a 90-degree angle there, and the head to tail method of drawing vectors is obeyed in this case. Right, a quick check, and then you then calculate the magnitude of the y component using the sine theta function, 47 kilometers, which is the hypotenuse times sine of the angle. Sine negative 60 degrees will give you negative 40.7 kilometers. For the direction, notice how the y component is pointing downwards, and therefore that's consistent with a negative j hat direction. All right, so now that you've obtained the x and y components, you then add the x components together, giving you 23.5 kilometers I hat, and add the y components together, giving you negative 18.7 kilometers j hat. You then arrive with just a single x component and a single y component for the displacement delta x, which is also the resultant vector. So you can quote your answer. You can write your answer by writing down the x component, 23.5 kilometers I hat, and the y component minus 18.7 kilometers j hat. So this is a valid way of putting the final answer, and it's acceptable. You can get the full points by writing this as the final answer, or if you want to write your final answer in the form of magnitude plus direction, you then need to work out what's the magnitude of this resultant vector and the angle theta that gives the direction, right? Angle theta here giving the direction. So for the magnitude, it's the hypotenuse of a right angle triangle. Pythagoras theorem says x component squared plus y component squared. Then take the square root of that, will give you the resultant vector or the magnitude of the hypotenuse, which then gives you the displacement. And for the angle, use the tangent trigonometric identity using the tangent theta function, or arctangent of the y component divided by the x component. You'll get negative 38.5 degrees. Okay, your resultant vector is in the fourth quadrant, so you can leave your angle as negative 38.5 degrees, or if you want to do 360 minus 38.5 degrees, that will be a valid angle as well. Right, so you can write down your answers either in this component form or in this polar form. So we call this the polar form of writing vectors. This is the component form, and both answers should be correct. Okay, so you can write the vectors as a sentence, right, giving the magnitudes and the direction. You can also use an arrow with the correct length and the correct direction indicated by the arrowhead, or you can use this, brackets to indicate the magnitude. You can use the component form or the polar form. These are all equivalent ways of writing the same thing, and they are all acceptable for the tests, unless you are specifically asked to write the vector in a specific form. Right. So there is an exercise that's available for you to practice on. You can find it in the PowerPoint slides that's posted on stream. We're given two vectors and you're asked to add them, subtract them, add them, subtract them using these different scenarios here. The solutions are also up on stream. But I would say that you try out solving the problems first and then look at the solutions. All right, so that concludes our lecture on vectors, how to add vectors using the component methods. Firstly, by finding the x and y components of a diagonal vector, and then figuring out the resultant vector magnitude and direction.